Okay, a few of you guys wanted to see another example of the average atomic mass where we have two unknowns. So I felt like why not do another version of this? This is one that was actually off that optional worksheet that I gave you. I know it's done online if you follow that website, but still, maybe just seeing it spilled out in front of you might help. Okay, first things first, my software is not up to what I'm used to. I guess not up to par what I'm used to using. So I don't know exactly how well this is going to draw. This is actually a first for me with this particular software. We don't have to talk about it. It has to do with upgrading OS X to Yosemite, but let's not get it there. Okay, reading the problem first. I guess I should start with that. Let me erase that. Calculate the percent abundance of Fe57 and Fe iron 58 given the following data. And you can see that we have this data table that's very similar to the tables that I always did for our problems. And note that we have two unknowns, okay, two unknowns for percent abundance for iron 57, iron 58, which have a specific mass 56.9354 and 57.9333. We don't know those percentages, and that's actually what they want, the percent abundance. They want those question marks filled in. But they didn't give us what the average atomic mass is. And it seems like maybe they're steering us in the wrong direction of not giving us enough information. And it would be up to you to then pull up the periodic table and see that iron has a uh, average atomic mass of 55.845. So that's that needed piece of information when you're going to do this problem that you have to know that when you combine all of these, right? If you combine the decimal form and the weights, okay, and our decimal form is going to be 0.05845 and 0.91754. And here's the problem with the software. It is massive, and these problems do fill up the whole board, so I don't know how that's going to work. I'm not going to do X and Y, and you know what? I'm going to do A and B. Just because the X's and X's sometimes look like multiplication signs. When you multiply these out in our average atomic mass, it spits out the answer that was on our periodic table, which we just said was 55.845. So that's the actual answer that everything has to multiply out to equal. That's iron's average atomic mass. Okay, and it actually makes sense that it's in the 55.8, almost 56, because most of that population, right, most of the percent abundance does come from the 56. So it's going to be very dominating on the mass. All right, so if we are going to erase, and here's another problem, I have to erase the whole board, which is massively unfortunate. Just to throw this back in, and then we're going to get rolling. Five, 4, and then I said that was an A, that was a B, there's a 0, there's a 0. Okay, so setting this up, I would have my mass times the decimal form. So I'm going to have 53.9396, multiplied that by 0.05845. Add that to the 55.9349, and we'll multiply that by that's a multiplication dot, that's a multiplication dot. Maybe I should use X's, guess I should. Now they really look bad, and I can't erase, I don't know what to do, I have to live with it. Okay, 91754. So that's the first two players, the iron 54, the iron 56. Okay, so I got this times that plus this times that. And here's where the algebra comes into play, because I'm going to have this times A and that times B, right? The 56.9354 is going to be times A, so I'm going to add that up. 56.9354A plus 57.9333 B. And we said all of that equals, and this one might be rough, 55.845. That was off the periodic table. 55.845. I'm massively impressed that I got that in there. Okay, so that is actually an equation that's set up. I have my two variables, A and B. I have all my known stuff. I know it looks a little messy. It's just par for the course with this tablet. I have this multiplied together, which is the top two. And I have these two multiplied together, which is the 56 information. Then I have my A, then I have my B. And there is no math that will get you the real values for A and B right now. There is no math that can solve for a two variable system without a little help, and we have to help this along. Okay, and we do know one thing. We do know that by definition, percent means out of 100. Right? The word percent implies 100%. It doesn't imply, it just means it. So one thing we can use is that information to find another equation. Okay, the second equation is actually the easy one. It's very commonsensical. It's the one that's hard for a lot of us to see. Now, if these add up to be 100, how did you get to decimal form? Well, you took the number and you divided by 100, right? 91 turns into 0.91. So if all of these add up to be 100, then in decimal form, all of these add up to be equal to 1. So I'm going to do that. And I'm going to add up all the decimal forms. Try to give myself some space. 0.5845 plus 0.91754 plus A plus, my goodness, am I good with the spacing? B. Another huge accomplishment. So these two seemingly independent equations are not that independent. What I mean by that is they share A and B. The meaning of A and the meaning of B are the same in both equations. In mathematics, we call this a system of equations. Okay, and it's very powerful. There's several ways you can actually use both equations to solve what A and B are. The method that we use, or that we used in class, was this whole idea of substitution. What substitution was, if I take one of, and it actually doesn't matter which one, if I take one of these equations and solve for A or B, I can then substitute that variable into the other equation. Now, solving the top one for A or B gets a little messy, but solving this bottom one is actually not so bad. So if I was going to solve for A, hopefully you can see that A would be equal to 1, and then all this other stuff is going to be minus. Right? Subtract both sides, 0.05845. Just combining like terms, 0.9, there's a 0 in front, 0.91754 minus B. Right? I have to subtract everything to isolate the A. I have some like terms here. I have 3 of them. 1, 2, 3. I can subtract off my 1 to get 0.02401 minus B. Okay, so we still don't have any clear-cut evidence of what A or B is. We have this, we have A equaling 0.02401 minus B, but that doesn't really tell us anything. And here's where the magic happens. And I apologize, just giving you a heads up, I am going to erase the entire screen in just a few seconds. It's the only way I have to work right now. But what we're going to do is, these were independent equations. First of all, I hope you see that this equation is the same thing. All right, I just cleaned it up and solved for A. So we have this equation and the top equation, the main equation. And they're independent equations, so this A is the same. They're independent, but this A is indeed the same as that A. They have the same meaning. So if I take this information here and I plug it into there, what's going to happen? Well, before we do that, take a look. We have, I'm just squiggly line read, okay? I have numbers, 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 numbers. I can make sense of that. I have numbers, 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 numbers. I can make sense of that. I have numbers here, 56.9354, that will be multiplied by what's circled, the 0.02401 minus B. So that will have numbers and a B, plus numbers and a B equals a number. All right, so what I'm going to do right now is I'm going to rewrite the entire thing um, and try to squeeze it in with this new substitution in for A. So our A is going to disappear. It's going to be only in terms of B. Okay, the one thing I am going to have to do just for space is I'm going to have to multiply these out. That's a regular number. Multiply these out just for space purposes. So what I mean by that is when I crunch those numbers of these two multiplied together, right, the decimal form that was there, the 0.05845, I received 3.1528. When I multiply these two together, right, the 0.91 times the 559349, I received or calculated 51.323. And then this one had the A, but A is gone, right? I had the 56.9354 times A, but A is gone. A was substituted in for what we solved A to be in the other equation, right? Substitution system of equations. 0.02401 minus B. Okay, and then we had our other term that was at the end. This one times our B that was there. Okay, so I have my 57.933B equals, and I think I can squeeze this in one more time. Oh boy. 55.845. Okay, now we have a system of equations where, I'm sorry, we don't have the system of equations. We have one equation with one variable. Okay, A is gone. We substituted A out for that B term from the other equation. So now all we have to do is solve for B. Okay, first of all, you should be able to see that the like termsness of this term and that term, they can be completely added up. Okay, and this term also can be added up. So what I mean by that is I can throw the 3.1528 and the 51.323 to the other side. All right, I can also distribute the 56.9354. Now, typically in the math, we like to factor. This looks like it's already factored out, and that's great for a lot of cases in math. In this particular type of math, we don't want it as factored because we want to have access to that B. Right now, the B is locked away in the parentheses. We need the B to be out in the open so that I can combine it with this B. So I'm gonna distribute that 56. Okay, and when I do that, and you know what, I'll try to write everything out one more time. 3.1528, try to write a little smaller this time because I am going to run out of room. 51.323 plus, and here comes the magic, 1, right? This is going to be a small number. 56.9354 times 0.02401 is 1.3670 minus 56.9354. B, there's a subtraction in there, right, for the minus, plus 57.933. Was there 3 threes? Okay, there was supposed to be 3 threes. So I'm sorry about that. 33B. And again, I have to squeeze in my 55.845. Awesome sauce. All right, now we have almost all of our like terms out there. There's no more parentheses. Now we can just start combining things, throwing terms, combining them together by like terms, throwing them from one side to the next. Okay, and when I do that, hopefully you can see that I'm going to add these two B terms up, and I'm going to have 0.9979B equals, after I do my 55 minus, 55.845, and I subtract all three of these, I get 0.0022. And yeah, that works for me. And then I finally solve for B, which is up here as Almost, it actually is the same number, 0.0022. All right, now, what does that mean? Well, we have B. So we know that the percent is actually 0.2% for B. Well, what about A? Well, we go back to that system of equations. All right, so I'm going to clear this out right now. And I'm going to say that right here, if I remember correctly, it was B was, I'll just look down and look at it, 0.0022. One of our system of equations was A equaled 0.02401 minus B. That's right before we substituted in. Remember, this was what was in parentheses. So if we substitute that B into that B, we'll find out what A is. When you do that, you get A equaling 0.0218. Okay, so if I put my decimal form back in here, okay, that's a C. You'll see that this was 0.05845. This was 0.91754. And now we have A being 0.0218. And we have B being 0.0022. Our final answer here will be, there's the bell. Our final answer, you have to, we divided by 100 to get this way. We have to multiply by 100. This one turns into 2.18. This one turns into 0.22. Those are the actual percents that are my answers. Okay, that's the answers. Softball announcement, Paul T. Bear. Sounds good. I don't know if you guys can hear that. Okay, that's the final answer. Now, there's, wait, other announcement. Counseling office, Ella, okay, got it. A good way to check this to see if you're right is to indeed add these up to see if they're 100. When I added those up in my calculator, I got 99.999, which meant that I'm pretty much right on the money. Another way to check would be to multiply all of the decimal form times the masses and make sure after you do that calculation that you get the periodic table value of 55.845. Okay, so that's not a Y, that's a 4. So there's ways to check to make sure that you did this correctly. Both checks, this one's actually much easier, will give you a really good indication if you did it correctly. And it looks like we did it correctly, so good for us. And that be average atomic mass with the unknowns for the percents. Okay, and this is as hard as it will get for that.